A final exam type of confidence interval question will try to see if the student knows when to use the z-distribution and when to use the t-distribution. Stick around because I'm going to show you how to get full credit and even partial credit if you mess up. As long as you remember a few key words, you'll be fine. So in a Stats 1 college-level statistics class, most likely you're going to get on your final exam a confidence interval for a single population mean. And it's most likely going to be a word problem. And there are a few key words that you're going to need to identify. So it's going to say some stuff and give you some context, and probably, it's not even that important to read that stuff. But then it's going to say something like, based on, and it'll say a certain number of observations. So let's just say based on 10 observations, a mean of, and it's going to give you some kind of a number. I'll pick a number just off the top of my head. How about 69.96 was observed. And this observed is a key word. Might not say that. It might say a mean of 69.96 was calculated. However, observed is the statistical language. And if you see calculated, most likely your professor doesn't have formal training in statistics, but you could certainly see that. You might actually see the word estimated. And that's a good statistical word. And all these indicate that this is a sample mean. Now, what else would it be? Now, you could say well, could it be the population mean? Well, no, because you wouldn't estimate a confidence interval if you knew the population mean. That would be a waste of time, energy, money, effort, right? So these are examples of an estimation process, of an observation process. And with the sample mean, it's pretty easy. So based on 10 observations, a mean of, say, 69.96 was observed. Then it's going to say something like the standard deviation and it's going to say a bunch of different, it could say a bunch of different words, was, and it might say known to be. It might say assumed to be. It might say calculated to be. It might say observed to be. And it might say estimated to be. These are the words that will be thrown at you. And if in this final exam word problem it says the standard deviation was known or assumed to be, this is the population standard deviation. And with this, you will be using a Z confidence interval. So in a different color, I'm going to write UZ. Use Z. However, if the problem says calculated to be, or observed to be, or estimated to be, then you're going to be using what's called the sample standard deviation. And the symbol for that is a little s. Not a big S, but a little s. And it won't matter if your professor is not formally trained in statistics. It doesn't matter whether you use a lowercase or an uppercase s. But if your professor is formally trained in statistics, make your s a little bit on the small side because it matters. Now, the general formula for the confidence interval has a little bit of tricky symbolism, which I'll get to. First of all, let's call this the 1 minus alpha. And this is a Greek letter alpha, not a 2. One minus alpha times 100% confidence interval for the population mean. Now, the symbol for the population mean is the Greek letter mu. Sometimes the population mean is called the true mean. Or the population mean. And this alpha, this Greek letter alpha, represents something important in statistical hypothesis testing, which if you've watched some of my other videos, you know I don't want to get into that at this exact moment. But this 1 minus alpha is called the confidence level. And sometimes it's called the coverage probability. Coverage probability. So the whole 1 minus alpha is the confidence level or the coverage probability. And 1 minus alpha is expressed as a decimal. Let me write that down for you. So 1 minus alpha is a decimal. But once you multiply that decimal by 100%, you've converted it into a percentage, basically by moving the decimal point 2 places to the right. So this is the label of the confidence interval formula, which I will get at shortly. Now, let me tell you the two formulae that you'll have to deal with. One uses the z distribution and one uses the t distribution. So we have x bar plus or minus z sub alpha over 2 sigma sub x bar. And we also have x bar plus or minus, now instead of a z here, we have a t sub alpha over 2 with n minus 1 degrees of freedom. Degrees of freedom. Sometimes this is just symbolized by df. Times s sub x bar. And this is a lowercase s. Now, you'll notice that the formula, in terms of the way it looks, is essentially the same. So this x bar is the sample mean. And you'll notice that this x bar is the same in both formulae. Okay. The z sub alpha over 2 is a single symbol. And this t sub alpha over 2 with n minus 1 degrees of freedom is also a single symbol. And where do we get this baby? We get this from a t-table. also known as student's t-distribution. Where do we get this? Well, obviously, we get this from a z-table. And this is called the student's t-distribution. This z-table is called the standard normal distribution. Now, some people will call this z value and this t value, we will call this a critical value. Critical value. And a critical value is actually a little bit of a fancy term for a percentile. It's nothing more than a percentile. That's all it is. Now, you all know what a percentile is, because if I said, look, little Johnny got an 89th percentile in his SAT, you would know that little Johnny's score was at least as good as 89% of the people who took that SAT. So you know what a percentile is. So that's what this z sub alpha over 2 is, and that's what this t sub alpha over 2 with n minus 1 degrees of freedom. Let me be really clear here that when we have alpha over 2, this is an alpha, this is a 2. Some of my students get a little confused and they say, is it alpha over z? No. Is it 2 over z? No. It's alpha over 2. And that's why when I draw my z's, I always put a little line through it so that I know that it's a z and it's not an alpha and it's not a 2. So I would recommend you all putting little lines through your z's. Would definitely be recommended. So this comes from a table, which I'm going to show you how to get. And this term over here is called the standard error of the mean, SEM, standard error of the mean. And this is called the observed standard error of the mean. I'll just write OSEM for observed standard error of the mean. Now, some people will call it the estimated standard error of the mean. You could use either observed or estimated standard error of the mean. But that's the only difference here. This is the standard error of the mean. This is the observed standard error of the mean. Some people also call it the sample standard error of the mean. And I do apologize from the bottom of my heart that statistics has all these synonyms, but so does whatever language you speak has synonyms. Synonyms are just a way of life. Now, I should tell you that the standard error of the mean is equal to the standard deviation of an individual observation divided by the square root of the sample size. That's what it is. And the estimated standard error of the mean is equal to the estimated standard deviation divided by the square root of the sample size. So the only difference between the term using sigma and the term using S is that the term using S is observed, estimated, or sample. These are the words that you just have, these keywords that you have to know. Observed, estimated, and sample. And your professor will probably throw these words at you. These are the key words to tell you to use the t-distribution formula. And the words that tell you to use the z-distribution formula are either known or assumed. These are the key words. So now we've reached the stage in this video where you will know which formula to use. You're either going to use the Z distribution or you're going to use the T distribution, and you know the key words. Now, the next part I'm going to have to show you is actually doing this with an example, and I'll give you an example of both to tie this up. And I'm sorry the video is long, but it's a long concept, and that's what we are going to do now. So a professor who likes free response questions and likes to give, partial credit and see how their students actually do things might frame it this way. You'd get a bunch of words establishing the context, and then somewhere it would say, observes a mean of, let's say, 69.96, based on, let's just say, 10 observations. And now we have this key word, observes a standard deviation of, say 18.43. And then it's going to say, calculate and interpret the 95% confidence interval for the population mean. So if you recall, I told you that the way we can determine whether to use the Z distribution or the T distribution are in these key words. So notice here we say observes a standard deviation. And I said if it says something like the standard deviation is observed to be, or calculated to be, or estimated to be, these are the key words that tell us to use the T distribution. So I'm going to write this down for you. And so the formula is going to be X bar plus or minus T sub alpha over 2 with n minus 1 degrees of freedom times lowercase s sub X bar, which is the estimated or observed standard error of the mean. Want to remind you that this is a single symbol which comes from a statistical table, and this is a single symbol that comes from a formula. So let's put this stuff in. So observes a mean of 69.96. That's this. This one's easy. Let me do this one here. So this, the estimated standard error of the mean is just the estimated standard deviation over the square root of the sample size. So that we can just put over here. So that would be 18.43 divided by the square root. And it says right over here, it says 10 observations. So that would be 10. And I'm just going to draw a little arrow so you see where the 10 comes from. And I'm going to draw a little arrow here so you see it from the formula. And here's the 18.43. So the only thing left to find is this percentile or this critical value. And I want to show you a little picture of what this should look like. So this would be a T distribution. Now this n minus 1 degrees of freedom, n is equal to 10. So n minus 1 equals 10 minus 1, which equals 9. So this is a T distribution with 9 degrees of freedom. And if we have a 95% confidence interval, that means 95% of the area under this probability density function, which is a T distribution with 9 degrees of freedom, it's going to be within these two bounds. This score here is T sub alpha over 2, and this score here is negative t sub alpha over 2. Now in this case, we can see that this is a symmetric distribution, and since it's symmetric, there's going to be the same amount of area to the left of this t-score as there is to the right of this t-score, namely 2.5% of the area will be to the left and 2.5% of the area will be to the right. So all we have to do here is just find that t-score that has 2.5% of the area to the left. Or we could use that t-score that has 2.5% of the area to the right. Now it depends on the table that you have. So here I have a little book, which I'm going to turn to the back to where the table is. And I want you to see over here that this table says selected percentiles of students' t distribution. And we have 9 degrees of freedom. And we want 2.5% of the area to the left. So that would be the 2.5th percentile. With 2.5th percentile that we're using is equal to negative 2.2622. So this is a symmetric distribution. So this is going to be negative 2.2622, and this is going to be positive 2.2622. So now all we have to do is put the proper critical value into this formula and just put it into the calculator and crank out our lower and upper bounds, and we're done with at least the first part of this, which is the calculation part. So this t sub alpha over 2 with n minus 1 degrees of freedom, this is 2.2622. So I'm going to put this into the formula right here, 2.2622. And I want to call your attention to one little fact that you should know. This negative t sub alpha over 2 is actually the 2.5th percentile. And this positive t sub alpha over 2 is actually the 97.5th percentile of the t distribution with 9 degrees of freedom. Now, I think it's pretty obvious where I got the 2.5 for the 2.5th percentile. But what I want to show you is if you take 95 and you add 2.5, this gives us 97.5. So this is where we got the 97.5th percentile. Because if you look at this t distribution, this t sub alpha over 2 score is at least as large as 97.5% of this population, which is called a t distribution with 9 degrees of freedom. So now that we have this simple formula, all that's left to do is plug this into the calculator, and I'm going to use the Casio FX300MS solar powered because it's my favorite calculator, and I own no stock in the Casio Corporation, but I just think it's really easy to use. So what I'm going to do, let me make sure this is in the frame. It is. So in fact, it might be a little clearer for you if I do this at an angle. I bet that's clearer. Yes. So what I'm going to do is I'm going to type in 69.96, and then I'm going to hit the minus button. Now, why do I hit the minus button first? Because we read from left to right. And so if we hit the minus button first, we can get the lower bound of the confidence interval first. So I'm going to subtract 2.2622, and I'm going to hit the times button, and then 18.43, and then the divided by button, and then the square root button, and then the 10, and then I'm just going to hit equals. And because this Casio calculator is such a well-designed calculator, I didn't even have to mess around with parentheses for the radicand of this denominator. It's just it's a really great calculator to use. And this tells us that the lower bound of this 95 confidence interval is 56 point, now I'm going to round this 7 up to an 8. So 56.78, I want to write that down. That's the lower bound. Now let me show you how easy it is to get the upper bound. So what I do is I take this little button over here, because I don't want to type this whole thing back in. I mean, basically, I don't like doing any extra work. So all I'm going to do is I'm going to change this minus now into a plus. And this nice little calculator will just overwrite it if I just hit the plus button. And now I hit the equals button, and everything else is the same, and I get 83.14. So let me put this out. 83.14. Now, some professors might want you to put this on a number line. I mean, I don't know. I don't. But, some professors might want you to actually put this on a little number line and write 56.78 over here and 83.14. And that's the first part of your answer. This is the confidence interval. This is the 95% confidence interval for mu. So when it says calculate, we've done half of the question. Right, so I'm going to put a little check here. This is the answer for the calculation part. But then it says something over here, which the type of professor who's into the free responses will want you to actually interpret this in your own words. Whereas the sort of professor that's more into like objective evaluation and treating everybody completely equally might use a multiple choice question where they give you different interpretations and you have to pick the correct one. But either way, on a final exam in a Stats 1 class, you will almost definitely have to interpret a confidence interval like this. So I want to write down the interpretation for you really clearly, because students lose credit on this all the time. So you should say something like this. And I'm putting quotes because if you say it this way, you will get full credit. So if you say there's a, or I meant to write A, but I wrote 9 because I was all about to write 95%. There is a 95% probability that the aforementioned I love this word, aforementioned. It means what you just calculated. Aforementioned. I love this word. That the aforementioned confidence interval will capture. Now, this is the word I like, capture. The true mean. And if you really want to show your professor you really know what you're doing, the true population mean. Now you could You could also, instead of using the word capture, you could use the word cover. Like I told you before, this 1 minus alpha 100%, which in this case is 95%, is sometimes called the coverage probability. So the idea here is that if you were to replicate this estimation process where, we collected data and we estimated the sample mean, we got this critical value, we used this formula, we did this thing, we got this whole thing. If you were to replicate this process, let's say 1,000,000 times under different, performing the same experiment, 1,000,000 times, you'd be getting different confidence intervals and they'd be moving around. And if you looked at this, right, somewhere is the true mean, also known as the population mean. And we'd be getting confidence intervals that'll be moving around. Some will be larger, some will be smaller. They'll be moving around as you repeat this experiment over and over again, collect different data, and they'll be moving around. And this is the idea, right? So what we're saying is there's a 95% probability that this confidence interval will capture the true mean. 95% of the time, these replications will capture the true population mean. Sometimes it's not. Sometimes it's not. But most of the time it will. So that's the idea of the confidence interval. Now, the reason why you have to write it this way to get full credit. You will lose credit if you say something which a lot of students say, and most professors will take credit away from you. A lot of students will say something like, there's a 95% probability that the population mean will fall inside of the interval. That is wrong under standard classical statistics that's taught in Stats 1. That's wrong, because if you look at my little demonstration here, low tech as it is, with fingers representing the bounds of the confidence interval, each time we do an experiment, we'll calculate a confidence interval. Here's the first experiment. Here's the second experiment. Here's the third experiment. Here's the fourth experiment. Here's the fifth experiment. So each time we run this experiment, this thing will move around. But notice, it's the confidence interval, as we get different data, that's doing the moving around. This true population mean, it is what it is. It's fixed. The human being doesn't know this. I should probably write this down. Human doesn't know this. Let me move this up so it's in the field. Know this. I'll put a little exclamation point here because I want you to think about it. If the human being knew what the true population mean was, why the hell would we collect data and do all this work to estimate the population mean when we just know what it is? So the human being doesn't know this. So as we replicate our experiments, this confidence interval is going to change. It's going to change its width probably. It's going to change its center. But 95% of the time, this confidence interval will capture or cover, you could use the word cover if you want, cover the true population mean. That's the correct interpretation for full credit. I would memorize it this way and say it this way on a test. There's a 95% probability that the aforementioned confidence interval will capture the true mean. And you can put this in parentheses, population mean, so that your professor knows that you know that the true mean is also called the population mean. And saying it this way, you understand this idea that as you go from experimental replication to experimental replication, you understand that this confidence interval is going to move. Its center is going to change, its width is going to change. But my test is tomorrow. How can I pick up some partial credit if I don't know how to do the actual math? 1. Indicate to your professor whether you'd use the z-distribution or the t-distribution and why by indicating the key word. 2. Draw a little sketch of the critical values. Even if you aren't able to get the exact critical values from the table, a little sketch will go a long way. 3. At least let your professor know that you know that there are n-1 degrees of freedom if you have to use the t-distribution. Not for the z-distribution, of course. 4. Write down that little statement about the coverage probability. Try to keep it as close to what I said as possible. 5. Indicate to your professor that the assumptions of both confidence intervals are random sampling from a normal or an approximately normally distributed population.